Herstein Abstract Algebra, 3rd edition, Chapter 2, Section 1, Problem 3. So for this problem, it's very similar to Problem 2. So if you need help understanding what this mapping T sub a comma b is, check out our video on Problem 2. Here for Problem 3, we're going to look at example 7. So this time our subgroup h of g, instead of restricting a to positive or negative 1 like we did for Problem 2, we're going to restrict a to the rationals, and we want to confirm that our subgroup H, with the operation it inherits from G, is still a group. So A is rational and B is real. Here we see our group operation T sub A B star T sub AC is expressed in that form there, AC comma AD plus B. What do we need to know here? Again, reminder of what a function or a mapping is. These are elements of our set G. So each element is itself a mapping of the form AR plus B, where A is restricted to the rationals, R is a real number, which is our input variable, and B is real. We have our definition of a group, which is what we'll be checking for this problem. And then our two claims at the end there, when we combine rational numbers, we get a rational number. And if you combine a real and a rational number, you're always going to get a real number back for sums and products specifically for us. Looking at our solution here, we just need to check the 4 axioms to be a group hold for our subgroup H. Number 1, H is closed. This is where we take any 2 members of the subgroup H, we combine them with the star that it inherits from the group G, and show that the new element is still an element of H. So here, our operation star gives us T sub AC comma AD plus B. So what is the condition to be a member of H? The first subscript there needs to be rational, and the second subscript needs to be real. A and C, by themselves, we both know are rationals. That's our assumption that we started with 2 elements in H. Remember, to be in H, your first subscript has to be rational. So A times C is the product of 2 rational numbers, which by our claim yields us a rational number. The second condition to be a member of H is that the second subscript is a real number. Here, again, A, D, and B are all real or rational because we got them from members of H. So when we take their product and sum, we get a real number back, and we conclude that H is closed. Number 2, H is associative. So here we just need to check that our operation, we can apply it in any order of operations as far as those parentheses go. We do this on the left side and the right side. Note, this is exactly the same calculation as problem number 2. Restricting H to different subgroups there didn't affect whether it was associative. Number 3, is there an identity element? So an identity element is an element E such that A star E equals A and E star A equals A. Remember, we need to convert that notation into how elements of our group are represented. So we represent elements of our group, H, with this capital T sub 2 lowercase letters. So here we pick one element, A comma B, to be our any element in H, and then I'm letting E equal T sub G comma H. Again, I could use any letters there. My identity element's going to be T sub G comma H, and we need to solve for G and H. So we do that, and we find that in order for the left-hand side to equal the right-hand side, component by component, AG has to equal A, which means G is going to have to equal 1. And for AH plus B to equal B, H has to equal 0. Now we need to confirm that when we multiply in the other direction, that we get the same identity element. And we do that, and again, we find that G equals 1 and H equals 0 is the unique solution. Therefore, T sub 1 comma 0 is the identity element of H. Our last axiom to check that this is a group is the inverse condition. So again, that is, we can always multiply by a unique element on the left and right to get back to the identity element. So here, how we express that is T sub A comma B star T sub C comma D equals our identity element, or we flip the multiplication around from left to right. Again, we're considering T sub A comma B as like a given element, and then we're solving for C and D here. So if I give you any element T sub A comma B, is there a unique T sub C comma D in H such that right and left multiplication get back to the inverse? So here we do that, and we see that in order for our equation to hold, AC has to equal 1, and AD plus B has to equal 0. And then we can just solve for C and D, and we get C equals 1 over A and D equals negative B over A. Now, we're not done. We need to make sure that this element is a member of H. It is very possible that the inverse you solve for would not be an element of the subset that we're working in. So we need to make sure that 1 over A is rational and negative B over A is real. And then finally, we need to make sure that if we multiply in the other direction, we also get back to the identity, which we do.